Okay, so now I want to look at a classic example in first year physics, which is called the ballistic pendulum. So it involves a pendulum. So in this case, let's say a block of wood, which is hanging from some rope from the ceiling. And the idea is ballistic. You got a bullet. So there's a bullet coming in, moving really fast, and it slams into that block of wood, burrows itself in, it comes to rest with respect to the block of wood. So now you have a bullet block system, but that's moving. Conservation momentum says the original quantity of motion of the bullet is now stored in the block plus bullet system moving to the right. And then it's attached by ropes to the ceiling, and so it swings up to some height before momentarily coming to rest. And we just measure the height that it swings up to before momentarily coming to rest. And there's a relationship between the height that the pendulum swings up and the original speed of the bullet. Okay? And so this is sort of like, in the days before high-speed cameras, this is a super low-tech way of measuring something that's moving so fast you can't see it. It's a very simple device. But what's nice about it, it's a great illustration of the fact that energy is always conserved and momentum is always conserved. Okay? And we're going to solve this problem using both conservation of momentum in the form that delta P total is equal to 0. So if you have an isolated system, momentum can go down here, but it has to increase over here, so the total momentum never changes. And it also involves conservation of total energy. And we'll apply that principle in the form of, if the energy over here goes down, the energy over here must go up, so the total energy in an isolated system never changes. So delta E total is equal to 0. So the real emphasis here in this problem, and you've got a bullet slamming into a piece of wood, and so there's tremendously strong forces acting, forces of friction or deformation. There's a tremendous amount of heat generated, thermal energy generated. It doesn't matter. Whenever thermal energy is generated, friction is involved in any circumstances whatsoever. It is always true that momentum is a conserved quantity and energy is a conserved quantity. Okay, there's never a violation of that in any situation, including situations that just involve friction or thermal energy. So the key point of this problem is that energy and momentum are strictly conserved quantities. Okay, that's the emphasis of this problem. Okay, so here's how it works. So we start off with a bullet. So there's a bullet. So an object of relatively small mass, which is moving very fast to the right. Okay, so this bullet has some quantity of motion stored in it, some momentum stored in it, mass times the velocity. And then the idea is that bullet hits a block. So this is a block of wood, let's say. And this block of wood is of some much larger mass, m, let's say. And it's initially at rest. The bullet lodges itself into that block, like it'll just really bore a hole right into it. And then so the bullet will bore a hole in, and the bullet will end up lodged inside that mass big M. So this object now is an object where the bullet is at rest with respect to the block. It is an object of mass big M plus little m. And because of conservation of momentum, as we'll work out, of course, this object over here has to now, after that bullet comes to rest in the block, that whole thing is now moving with some velocity v to the right. Let's call it capital V to the right. But that velocity will, of course, be smaller. Okay, so this just illustrates the idea that momentum is conserved. So the momentum of this object is a small mass moving with a high velocity. That will have the same momentum as an object with a large mass, big M plus little m, moving with a small velocity. So what counts in nature fundamentally is not the velocity, but the momentum, the oomph of the motion, the quantity of motion, Newton's original quantity of motion. Okay, so now this guy, big M plus little m, moving with that slow velocity v, has the original momentum of the bullet. It's moving to the right, okay, and it's hanging from some strings from the ceiling here, and so it's going to swing up like this. it'll swing up and then swing down. Like the whole thing will just do this, right? After it gets struck by the bullet, it'll go like this. But what we're interested in is looking at it from the time that it was moving with speed v, its initial speed to the right, and then it swings up and then momentarily comes to rest. Okay, so it swings up, and so the strings go like that, and it has raised itself up through a height h. And then it becomes momentarily at rest. And so then the idea is you are going to measure the height h, which is something that's very easy to do, and then you're going to use conservation of total momentum and conservation of momentum and conservation of energy to determine the relationship between the height h that you measure and the original velocity of the ball. So this is the unknown that we're trying to solve for. This is the thing that we measure. But what's the relationship between v and h? How does v depend upon h? Okay, so what we're going to do is we're going to take this problem and we're going to divide it into two steps. Okay, so the first step is we're going to start with from here, where the bullet is moving with a speed v to the right through the air, and we're going to ignore air resistance. So the bullet is moving through a vacuum. Okay, and and from that moment in time to the time where the bullet, bores itself into the piece of wood and comes to rest with respect to that block. So little m and big M are now both moving with the same speed, smaller speed v to the right. So that's the first stage. Let's call that part A of the problem, is from here to here, so to speak. Okay, and then the second part of the problem says, well, now we've got an object of mass big M plus little m moving with a speed v to the right, and that thing is going to swing up a certain distance h before momentarily coming to rest. And so that's the second part of the problem. So we'll call that part B of the problem, is the swinging up stage. Okay. And now for both part A and B, we are going to apply both of these conservation laws. Momentum is strictly conserved and energy is strictly conserved. And both conservation laws for both parts will give us interesting things, interesting results to think about. Okay? So the first part is part A. Okay, so let's see, can I fit this here? So this is a one-dimensional problem. Okay, so we'll take the x direction to the right, and instead of writing vectors or components of vectors, x components, we'll just write it as p. And that really means px, the x component, or p total x or whatever. Okay, so the idea is we're going to apply conservation of momentum in the form of momentum of one object can go down, momentum of the other object has to go up, such that the total momentum remains unchanged. So without particular with regard to how the momentum is transferred. So we're going to apply conservation of momentum in this form. We're going to say that the change in the total momentum is always zero. Okay, and so delta P total, well, that means P total final minus P total initial. Okay, and then we say, well, what are these things? Well, in the final situation, we've got an object of mass big M plus little m moving with some unknown speed capital V to the right. So its oomph of motion, its quantity of motion, is mass times velocity. So big M plus little m times big V. Okay, so that's the final total momentum. Subtract the initial total momentum. Well, we have an object of mass little m moving with a much higher speed, little v, to the right. Okay. So that's that, and yeah, I can fit this in here. So conservation of momentum, there's a relationship between big V and little v. So this minus this has to equal 0. So you solve for big V, and it tells us that big V is equal to little m over big M plus little m times little v. And that's it. So you'll notice that in this situation, you've got definitely, friction forces acting, forces of deformation. That wood is being like split, right? I mean, there's strong, weird forces that are acting that we have no idea what they actually are, but it's completely irrelevant. Okay, momentum is a strictly conserved quantity. No matter what happens, no matter what the forces of interaction are, this must be true. So that's a very powerful result. We can immediately get a relationship between big V and little v, and it's that. And you can see that this relationship makes sense because you can take sort of limiting cases. So limiting cases would be, suppose that the block big M is huge in mass compared to the mass of the bullet. So then big M is much larger than little m. So in the denominator, you can ignore little m, and it's a little m over a big M. This ratio of masses is nearly 0. And so it says that big V approaches 0 in the limit that big M, the mass of the block, is much bigger than the mass of the bullet, which makes sense. If this is essentially infinitely massive, it's a brick wall, so to speak, attached to the Earth, well then, that brick wall attached to the Earth is going to have virtually 0 velocity after the bullet lodges in it. The other extreme is to imagine that this block isn't massive, really massive compared to the bullet. Let's just suppose it's made out of like, styrofoam or aerogel or something, and it's just super light. Okay, well then obviously that bullet's going to like lodge in there, and the whole thing will be moving at the same speed. So you can see in the limit, in the other limit, where the block has very small mass compared to the bullet, then this big M is negligible compared to little m. You can drop it out in the denominator, and it's little m over little m, that's 1. So big V approaches little v in the case that this block is very, very small mass. But of course what you want is a block of very large mass compared to the bullet, so that this block and bullet system is moving slowly, okay, and just rises up a little bit, okay, as a pendulum here. Okay, great. So that's what conservation of momentum tells us immediately. The second thing is conservation of energy. So we will write the conservation of energy law in the form of the total energy in an isolated system never changes. If it goes down over here, it has to go up over there. Okay, so 0 is equal to the change in the total energy of the isolated system. And so what's that? Well, let's see. So there are, the first thing we ask is, what are the various ways in which nature is storing energy in this problem? Well, one of the ways is certainly energy of objects in motion. There's certainly kinetic energy. So there will be kinetic energy, and there could be a change in that. But there's also going to be other forms of energy, most notably thermal energy. You can think of this sort of roughly as this bullet is boring its way, it's pushing itself really hard into that block of wood. You can think of it as very, very strong friction forces that are acting. And so friction, as the bullet moves through there, very strong friction force acting over that displacement transfers a lot of energy into thermal energy. So a bunch of thermal energy is generated. Okay, or there's the sound of this thing, bang. You can hear the bullet hitting. There'll be a sound emitted. So there'll be all kinds of other, basically the kinetic energy is going to go into all kinds of other energies as well. Okay, and so we'll just write that as plus delta E other. But I just want to make an important point that delta E other in this situation is mainly delta E thermal. The point is, when you do this experiment, you find that that bullet is super hot after it comes to rest in big M. And if this is a piece of wood, this hole that it bores into the piece of wood, it's just completely charred. Okay, so there's a lot of thermal energy generated in this thing. Okay, so yeah, great. So this is what conservation of energy says. And we can see from this situation, well, delta E other is going to be positive. And so what must happen is that the kinetic energy in the system, the energy stored in objects in motion, must have decreased, so that this negative thing plus that positive thing adds up to 0. Okay, so energy is always conserved, strictly conserved. So then we can work this out. Well, what is delta E other? Which is mainly delta thermal. Delta E other. Well, what is that? Well, it's just negative the change in the kinetic energy. Okay, so then we can work that out easily. So this is negative, so final kinetic energy minus initial kinetic energy. So the final kinetic energy is, we've got an object of mass big M plus little m moving with a speed big V. So that's 1/2 big M plus little m times speed big V squared. That's the final kinetic energy. The initial kinetic energy is a bullet moving with speed little v. So minus 1/2 little m times little v squared. Okay, and what's great about this is conservation of momentum immediately gives you the speed of the bullet plus block system, big V, in terms of little v. And then when you calculate change in the total, or change in the other energy, it involves a big V squared minus little v squared. That big V is immediately given in terms of little v. So conservation momentum then gives big V, and then you can figure out, well, how much of that original kinetic energy in the bullet went into other forms of energy. Okay, and so what you do is you just take this expression for big V, plug it in there. It becomes something squared times little v squared. Both of these terms are proportional to little v squared. And I'll leave this as an exercise for you to work out. It's one line of algebra. And what you get is 1 over 1 plus little m over big M times 1/2 mv squared. And remember that 1/2 mv squared, well, what's that? Well, that's the original kinetic energy in that bullet. So let's call that kinetic energy initial. That was in the bullet. Okay? And so now here's a really important point. In physics, we don't care about this number. What we actually care about is typically ratios. When you say, is that a lot of energy or a small amount of energy? Who knows? What you want to do is you want to compare the amount of thermal and other energy generated. You want to compare that to the original kinetic energy in the system. So what you really want to do is you want to work the ratio of delta E other. How does delta E other compare with the original energy in the system, which was just kinetic energy of that bullet? So you're asking the question, what percentage, what fraction of the original energy in the system, just kinetic energy, went into other forms of energy, mainly thermal energy? Okay, so that ratio, delta E other divided by the original kinetic energy, is 1 over 1 plus m over m. Okay, and so that's interesting. So for instance, suppose that, let's throw some numbers in here. Okay, so suppose that big M, just to make the numbers work out easily, is 9 times little m. Okay, so we want this block to be much heavier than the bullet, let's say around 10 times heavier. So then little m divided by big M is going to be 1 over 9 plus 9 over 9 is 10 over 9, and the denominator is 9 over 10. So this is 9 over 10, which means that 90% of the original energy in the system, which is kinetic energy in the bullet, went into E other, which is mainly thermal energy. Okay, so like I said, that bullet gets hot, and the surrounding channel that it moved through is hot and burned and all that stuff. Okay, so that's kind of cool. So we used conservation of, of momentum, and we used conservation of energy. It is always true that momentum, both momentum and energy, are strictly conserved quantities. So now we'll move on to sort of phase B of this example. And we're going to end up with a relationship between little h and the original speed of the bullet v. Okay, so for phase B, what we're going to do is we're first going to apply conservation of momentum to that situation. Okay, so you might think for a second, well, what we have is a block and a bullet moving with some speed v. There's some momentum in the system to the right, and then while that block plus bullet system rises up like this and comes momentarily to rest, has no momentum. Has momentum conservation been violated? No. The momentum, of course, goes into the earth. Okay, so let's look at this carefully. So we say, yep, so we know that momentum is always conserved. And so it's interesting to look at how that actually happens in situations. Okay, so we say delta P total is equal to 0. So let's see if I can fit these diagrams here. Well, let me put them, let's put them over here. Okay, so remember that in that when you have situations like, let me just use a simple example. You got a car driving along the road. So it's got some momentum in this direction. And then the car turns the corner. Okay, it goes around a curve like this and ends up moving in that direction. So the original momentum was that way. The final momentum was that way. Well, there's been a change in momentum of the car. Well, momentum is a conserved quantity. So the momentum of the car changed in, it used to be that way, and now it's that way. And so it changed in that direction. So if you take that vector and add a vector like that, you end up with a vector in that direction. So the momentum of the car the change in momentum of the car was a vector in that direction. Okay? And then you think, well, there must have been something else that changed its momentum by an exactly opposite amount to conserve momentum. Well, that's obviously the Earth. The Earth gained momentum in that direction. How'd that happen? Well, because in order for the car to turn the corner like that, the road had to exert a force on the car towards the center of the circle in that direction. Okay, so the road is pushing on the car in that direction, so the car is pushing on the road, i.e. the Earth, in that direction. So that force acting over the time the car takes to go around the corner imparts momentum to the Earth that way. So the change in momentum of the car is that, the change in momentum of the Earth is that, such that there's the change in momentum of the total system, car plus Earth, is 0. Okay, so in this system over here, what we've got is, so always keep in mind that very often in the day-to-day world, the Earth can absorb arbitrarily large amounts of momentum, okay, with very, very tiny changes in the kinetic energy. We'll talk about that in a minute. Okay, so in this situation, what we've got is the system does not just consist of the bullet and the block, it also consists of the Earth, because these strings attach to the ceiling, but that ceiling is attached to the Earth. Okay, so it looks like this. So you've got, here's the ceiling, so to speak. Let me try to fit this all on. Yeah, so this is the ceiling, and it is attached to the Earth over here. This is the Earth. Okay, and our original situation is, for part B here, the original situation is we've got a block of mass big M with a bullet inside of mass little m, and that whole thing is moving to the right with some speed, big V, and so this thing has some momentum. Okay, and that thing is attached to the Earth through those strings. So P, in this case, P total initial, which is equal to the momentum in the bullet, because the momentum in the bullet is equal to the momentum in the bullet plus block system initially, to the right like that. So P total initial, which is equal to mv, the original momentum in the bullet, well, that is, yeah, I want to say this. This is in the bullet plus block system. Okay, it's in this thing. Okay, and so now later on what happens is we have this situation where the pendulum is momentarily at rest. Okay, but it has but the block has swung up like this, and so the ropes are now at an angle like this, and this guy, the bullet plus block system, are at rest, and so there's no momentum in those guys. So where did it go? Well, obviously it went into the Earth. Okay, so now P total final, which is exactly the same as this momentum, which is exactly the same as that momentum, P total final, also equal to mv, is now in the Earth. So the Earth has absorbed the horizontal momentum of that of that bullet block system. Okay, so now that chunk of quantity of motion that was in here, stored in here, is now stored in the Earth. Okay, whatever, just imagine the Earth was originally at rest. Well, then after the pendulum swings up like that, the Earth is now moving a tiny bit, has gained a tiny bit of velocity to the right. And so there's a corresponding momentum to the right. And that momentum in the Earth is exactly the momentum that was originally in the bullet block system. Now you think, well, how? How did the momentum get from being stored in here to being stored in the Earth? Well, you know that there's been a momentum transfer from here to here. Okay, how? Well, momentum is transferred by a force acting over time. What force? Well, the strings. Okay, so if you look at those strings are under some tension. Okay, and because they are at an angle like this, as it swings up, there's a component of the tension force in the horizontal direction from both of those strings. Okay, so there's a force that's acting on this ceiling, okay, which is connected to the Earth, which is acting on the Earth. So basically, these forces, these horizontal forces, are pushing on the Earth, and they are acting over time. So if you take the T horizontal, whatever those forces are, they might be complicated functions of time. They're small when the pendulum is vertical, and then they grow as the pendulum swings up. It's a complicated function of time, and there's two of them. So that's the net force, horizontal force on the Earth. Integrate that over time from T initial to T final, however long it takes the block and bullet system to swing up like this. And that is the impulse. Force acting over time is impulse, is momentum transferred. So that is equal to mv. Okay? That's how the momentum from this guy is transferred to the Earth. But momentum is always conserved. And the Earth is a great absorber of any momentum. That's changes in momentum that are happening with things around the Earth. Okay, so the point is here that, this is a super important point, is that the Earth gains full momentum well, almost the full momentum, because remember that if the Earth is moving super slowly after this thing swings up, well, then that thing is also moving super slowly. So there's a tiny bit of momentum still in that thing, but the vast majority of the original momentum in the bullet is in the Earth. Okay, so the Earth gains the full momentum, and here's the key point. That's one key point. The second key point is but negligible kinetic energy. Okay, so we say, yeah, for sure, it's absorbed some momentum. But remember, kinetic energy is p squared over 2m. We're talking about the mass of the Earth here. And so mass of the Earth is big. It's in the denominator. So the amount of kinetic energy absorbed by the Earth is very, very tiny. Let's work it out. Okay, so we'll say, let's ask the question, what's the change in the kinetic energy of the Earth? Because we're imagining that the Earth used to be at rest in this situation, and now it's moving a little bit with some velocity we'll call VE. So change in the kinetic energy is then going to be 1/2 mass of the Earth times the velocity of the Earth, in other words, the velocity of the Earth gained as this thing swung up, squared. Okay? And then, this is super important. Kinetic energy is 1/2 mv squared. It's also p squared over 2m. Okay, get that in your head. Okay, so immediately write this in terms of it's the momentum, the extra momentum that the Earth starts at rest, has 0 momentum, say. Now it has some momentum. So it's the momentum of the Earth squared divided by twice the mass of the Earth. Okay? So then you say, well, what is the momentum of the Earth? Well, the momentum of the Earth is the momentum of this bullet plus block system at this instant of time. It's also equal to the momentum that the bullet originally had to the right. So the momentum of the Earth is P total final is in the Earth is just mv. So it's little mv squared divided by twice mass of the Earth. Okay? And then so what you do is you just rewrite this expression. You pull out one of these little m's divided by the mass of the Earth, and then you pull out the half. There's an extra little m because there's a little m squared there times a v squared. And then you see, wait a minute, what's 1/2 little mv squared? Oh, that's the original kinetic energy in the bullet. Okay? So this is equal to the mass of the bullet divided by the mass of the Earth times the original kinetic energy in the bullet. So yeah, the Earth for sure absorbs some kinetic energy. How much? Well, the original kinetic energy in the bullet, which might have been substantial, but it's multiplied by a ratio of masses, a dimensionless ratio of masses, which is the mass of the bullet compared to the mass of the Earth, which is basically 0. Okay, so this is approximately 0. Okay, for all practical purposes, it's 0. Okay, so great. So now we can, with that in hand, we can now think about conservation of energy in the form of, well, the total energy of an isolated system never changes. The system, the isolated system in this case, has 3 parts. It's the bullet, it's the block, and it's the Earth. Okay, so let's look at this. So 0 is equal to change in the total energy. Energy is always conserved. And we think, well, what are the different ways in which nature is storing energy in this problem? Well, so we're starting with going from here to here. So originally, nature is storing energy in the form of kinetic energy in this guy, okay, and then later on it's storing energy in the gravitational field because this mass has risen up through a height h. Okay, so basically there's energy of motion involved here. So there can be a change in kinetic energy of the bullet plus block, So the bullet plus block was originally moving with speed v, had some kinetic energy. Later on, it has no kinetic energy. So that's going to be negative. That's going to go down. Okay. There's also change in the kinetic energy of the Earth. Okay. But we just show that that's basically zero. For all practical purposes, this is zero. Okay. Plus change in the gravitational field energy. Okay, and because this mass has risen up through a height h, okay, there's energy has been transferred into the gravitational field, so the change in the gravitational field energy is positive. So this positive number plus that negative number adds to 0 in order for energy to be conserved. Okay, and so then we crank all these things out. So what do we get? Yeah, we can put it right down here. Okay, so the change in the kinetic energy of the block plus bullet system, well, change in kinetic energy is 1/2 m v final squared minus v initial squared. So this is 1/2. We have an object of mass little m plus big M, or big M plus little m, okay, times v final squared minus v initial squared. So the final velocity of the bullet plus block system is 0, minus the initial velocity is v. That's a capital V there, minus v squared. Okay, that's change in the kinetic energy of the bullet plus block system, and then plus the change in the gravitational field energy. And the change in the gravitational field energy is always positive. The mass of the object in question, which is big M plus little m, times the vertical height through which it has been raised. And so, or change, in this case it's positive change. Okay, so it's that. Yep. Oh, GH, sorry, M plus MGH. Okay, so then you say, well, what is big V? What we want is a relationship between little h and little v. Well, what is big V? Big V is just this ratio of masses times little v. So you take this expression for big V, you plug it into there, this thing plus this thing equals 0. It gives you a relationship between little h and big V. I'll leave that as an exercise for you to work out. And so what you find is, because I'm running out of room here, so what you find in the end is that little v turns out to equal 1 plus big M over little m times the square root of 2gh. Okay? So then you look at that thing. This is the relationship between little h and little v. So all you have to do to measure the speed of a bullet when you don't have a high-speed camera is to construct a simple low-tech apparatus like this, have the bullet lodge itself in to the block and swing up like this. Just measure that height. Easy. 5 centimeters or whatever. And then you plug it into this formula, and you know the ratio of the bullet mass to the block mass, and you can figure out the speed v. And then you can say, oh yeah, well, this thing makes sense because, this block on bullet will rise up through a certain height h, whatever that is, and then you're going to determine v. And then you can see that the result depends upon the ratio of big M to little m. The bigger you make the mass of the block compared to the bullet, the bigger the speed of the bullet was. And that makes sense because for a given height that this thing swings through, for a given height this thing swings through, the bigger the mass of big M, okay, the more gravitational field energy was increased, which means the more kinetic energy that this bullet originally had. Okay, and so as you crank up the mass big M, you should crank up the speed of the bullet. And you can see that that's in fact the case. Okay, so yeah, so that's great. So you measure h, and then that tells you what v is. So this is a great example. I love this example because in this example, you are convincing yourself that in any kind of situation whatsoever, energy is always conserved and momentum is always conserved. And in any problem, it's always a good idea to apply both of those principles. And along the way, each of those principles typically or usually tells you something interesting. So remember, in physics, we're not interested in solving particular problems with numbers here and there. We're just looking at a general situation and analyzing it as in as much detail and depth as we can, and basically learn everything we can about the system, everything that's physically interesting and relevant. Okay, so awesome. Ballistic pendulum.